In this paper, we study a problem of domain generalization via universal non-volume preserving approach. In this study, we narrow down the problem to a closed set problem. Particularly, scene training domain and unseen testing domain are the same characteristics in different contexts. For example, in face recognition, the scene training data is a normal lighting condition where the unseen testing data is in dark condition. The objective of domain generalization is to learn a robust classification in new unseen domains from multiple sources and training data. More than that, this paper aims for a single source domain generalization where the restrictive setting is that training data only comes from a single source domain. Our contributions in this paper are that we propose a novel framework for domain generalization named Universal Non-Volume Approach, UNVP, and an extended version named UNVP. In previous work, domain adaptation has been applied to transfer knowledge on a source model to a target model in either supervised or unsupervised manners. Particularly, domain adaptation tries to minimize the discrepancy of distributions between source and target domains. However, this method requires the target dataset during the training. On the other hand, in the context of domain generalization, we don't have target images during the training process. Domain generalization aims to learn domain invariant representations by aligning the distributions among different domains and matching the aligned distribution to an arbitrary prior distribution via adversarial feature learning. In our study, we define a problem of domain generalization as a worst-case problem around the source distribution. This formulation will guarantee good performance against data distributions that are distance rho away from the source distribution. In this paper, we propose the UMVP method, which is a new tractable convolutional neural network. Our method learns generalized deep features by modeling environmental features and discriminative features. Consequently, these learned features are robustly discriminative in new unseen domains. Additionally, our proposed framework is designed in the end-to-end style, which can be easily integrated into any other deep convolutional neural networks. In more detail, our proposed framework consists of two main streams. The first one is the discriminative feature model tries to minimize within-class distributions, and the second one is the generative distribution model. This network formulates feature representations to multiple Gaussian distributions. Finally, these features are incorporated to expand these distributions to new unseen domains. Learning UNVP involves two steps. First, we learn the discriminative feature model. Second, to train the UMVP model, we use a II stage training process. Specifically, the minimization phase updates the network according to the loss function and the maximization phase synthesizes new hard samples. In UNVP, we predefine means and covariances of distributions. Meanwhile, in a UNVP, we learn the means and covariances during the training process. Firstly, we investigate the effectiveness of hyperparameters in the ablation study. We use MNIST and MNIST-M as source training and testing data sets, respectively. To be easy, we use Leonard as a classifier. As a result, the smaller alpha needs more synthesis samples to adapt means and covariances. The larger beta helps to well adapt to new unseen domains, and the lambda assists to learn a robust model. We visualize the distributions of our methods compared to the standalone CNN on MNIST and MNIST-M datasets. While the standalone CNN obviously fails to model MNIST-M dataset, our UNVP successfully covers an unseen domain dataset. These sample distributions are completely class-separated when using our EUMVP. As mentioned above, our methods can be easily integrated with various CNN networks. We evaluate the robustness and the consistent improvements of the proposed UNVP and a UNVP with common deep networks. Intensive experiments have shown the performance of our methods has been significantly improved. We also compare our methods with other methods, specifically ADA, DAN, and ADA methods. We use MNIST as a source training dataset, MNIST-M, and SVHN as target testing datasets. The results have shown that our methods outperform other methods and achieve state-of-the-art results. We study our methods on the face recognition problem. In the experiment, we use extended Yale-B, CMU-PIE, and CMU-MPI datasets. For each dataset, we use the normal lighting condition as the source training dataset and the dark lighting condition as the testing dataset. As a result, our methods outperform other methods and achieve state-of-the-art results. We also do other experiments on pedestrian recognition. We use RGB images as the training dataset and thermal images as the testing dataset. Our intensive experiments on various backbone networks have shown our methods help to consistently improve the performance of standalone networks. We show our demo of pedestrian detection in thermal videos. In conclusion, in this work, we propose a novel framework for domain generalization named UNVP and its extended version UNVP. Intensive experiments have shown that our methods achieve state-of-the-art results in digit, face, and pedestrian recognition. Thank you for watching. Currently, almost deep learning methods assume the training and testing distributions are the same. However, in real-world scenarios, the testing data has been shifted far away from the training data. Therefore, deep learning models usually perform worse on new unseen testing domains,